today we're going to look at exponential growth and decay. So populations of animals, people, and bacteria usually grow in an exponential way, so hence growth. And radioactive substances and items that depreciate in value, such as the price of a car or I don't know, basically the price of most items, decay in an exponential way. So when we're talking about growth and decay, we need to be able to understand what the multiplier is. So how much, basically what are we going to take to an exponent to demonstrate growth or to demonstrate decay. So if we're talking about 10% growth, we want to be able to convert that to a decimal that we can use. So 10% growth, well, the idea of growth is that we're going to keep what we have. If we're going to keep 100%, and then we're going to add 10% onto that. So it means 100% plus an additional 10%. So if we look at that as a decimal, we know 10% written as a decimal is 0.10. So if we want 100% plus 10%, 100% is one whole. So we're looking at the multiplier 1.10 for 10% growth. Okay, for 8% decay, so that means we're losing 8% decay. So we're going to originally start with 100% or one whole, and we're losing 8% each time, which is 0.08. Don't forget that 0. 0.8, remember, is 80%. So we want to lose 8% each time, which means we're actually going to be multiplying by 0.92. We want 92% of what we've each time we go through one cycle, basically. Okay, 6% decay. So that's one whole minus 0.06. Again, don't forget that 0. So we're talking about 94%, or 0.94. And 11.3% growth. So here we're talking about one whole plus 11.3%, and that's going to give us 1.113. So that's saying 100% plus another 11.3%. Okay, so I'll show you how we actually use these multipliers. So to figure out the population after a certain number of years or a certain amount of time, we're going to start with the original population and multiply by the multiplier of the power to the number of years. So p sub 0, this here, we say that as p initial. So we'll have p initial times the multiplier to the number of years. The multiplier, remember, is what we just looked at here. So in this example, 1.10, this is our multiplier here, here, and here. Okay, so those are all multipliers. Okay, so example 1, we've got a species of bear introduced to a large island off Alaska where previously there were no bears. 6 pairs were introduced in 1998. It is expected the population will increase by 20% per year. So we want to find B initial, which refers to the initial amount of bears. So initially 6 pairs. Pairs refers to 2, so we know initially there were 12 bears. Okay, so in this example, we're going to have B initial times our multiplier to the power of n. Okay, we want to find the expected bear population in 2013. We should figure out what our multiplier is. It says the population will increase by 20% per year. So increase implies growth. So it implies we're going to keep 100% plus we're going to add 20%. So our multiplier is going to be one whole 100% plus 20%, or 1.20. Okay, so we want to know the expected bear population in 2013, They were introduced in 1998. We can simply just subtract that. You can even, these will all be calculator questions, by the way. So 2013 minus 1998 is 15 years. So we'll have, initially we had 12 bears. Our multiplier is 1.20, so that's telling us after each year it's going to increase by another 20% of growth, and we want that over 15 years. So we can plug this into our calculator. 12 times and we should get 184.84. 0.884. Obviously, we can't have 8/10 of a bear, so we can round our solution. So about 185 bears. So initially, we had 12 bears on that island. After 15 years, we should expect about 185. Okay, here we're looking at a radioactive isotope used in medicine, iodine-131. Its half-life or decay rate of 50% is 8 days. If a patient is given 25 milligrams of iodine-131, how much would be left over after 32 days or 4 half-lives? Okay, so this is a bit different. First of all, we can tell that it's decay, where our isotope of iodine is decaying over time. It's getting smaller. It's losing mass. So if a patient is given initially 25 milligrams, so this is our initial amount of iodine, we'll call it I initial, and it's decaying at a rate of 50%. So we're always going to lose 50%. So if we do our whole minus 50%, we know we're still going to have 50% left. So that's what goes here. And okay, so it says its half-life is 8 days, and we want to know how much is left after 32 days, which is 4 half-lives. So our amount of time, it's only going to lose 50% after 1 half-life. So really, this amount of time isn't always necessarily going to be in days or years. In this case, it's in half-lives, because we're looking at when is our isotope gonna reduce by half. Okay, and in 1 half-life, we know that's 8 days, and we want to know 32 days. So that's 4 half-lives, because we know 8 times 4, of course, gives us 32. Okay, so here's what we've got set up for ourselves. We can simply just plug that into our calculator. Oops. So 25 times 0.5 to the 4. Okay, and we should get about 1.56. And originally, our measurement was given to us in milligrams, so we know this is also 1.56 milligrams. Thanks.